Hi, my name is Seyed from EDD Academy, and today I'm going to be covering the integral test for sequences and series. Okay, so before we start doing the integral test for sequences and series, let's do some quick review and a practice problem. Calculate what the following series converges to. The sum from n is equal to 1 to infinity of 1 over n times n plus 1. So the way that we're going to approach this problem is that we're going to first write out an expression for the nth partial sum, which will look like the following. So S sub n is going to equal to 1/2 plus 1/6 plus etc. 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 plus 1 over n times n plus 1. So we can see if we plug in 1 here, we'll get 1 times 1 plus 1, which is 2, 1 over 2. Same thing if we plug in 2, we'll get 2 times 2 plus 1, which is 3, which will multiply together to form 6. All right. Using partial fractions, let's break down the nth term, which is this one over here. We'll do the regular procedure. We'll get capital A over n plus capital B over n plus 1, which will yield 1 over n minus 1 over n plus 1. We can now write out the partial sum in terms of the new expression for the nth term. So we got S sub n is equal to 1/2 plus 1/6 plus etc. 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 plus 1 over n minus 1 over n plus 1. So let's expand out the previous terms using this new formula. What I mean is that 1/2, when you're going to write it down in terms of this, is just going to be 1 over n minus 1 over n plus 1, which will be 1 over 1 minus 1 over 1 plus 1, which is 2. All right, let's group these together, all right, since they combine together to form the first term. The second term, likewise, it'll be 1 over 2 minus 1 over 2 plus 1, which is 1 over 3. And for reference, I've added in this term, which is 1 over 3 minus 1 over 3 plus 1, plus some stuff in the middle, plus 1 over n minus 1 minus 1 over n plus 1 over n minus 1 over n plus 1. So you've probably noticed the pattern by now. We can see that a lot of the terms will cancel out, leaving us with, okay, see 1 over 1 minus 1 over 2. However, there's a positive 1 over 2 over here, minus 1 over 3, but there's a positive 1 over 3 here, etc., with the minus 1 over 4 having a corresponding 1 over 4. And we can see that it works with the general formula as well, because 1 over n minus 1, it'll have a 1 over, it'll have a negative 1 over n minus 1 in the previous term. And this negative 1 over n will be cancelled out with the positive 1 over n over here. So all of the infinite terms in the middle, or sorry, n minus 2 terms in the middle, will cancel out, leaving you with 1 minus 1 over n plus 1, which is n over n plus 1. To calculate what this series converges to, we just take the limit of this expression as n goes to infinity. But just by looking at it, we can probably tell that this limit will equal to 1, since these have the same degree polynomial and their coefficients are the exact same. So we can conclude that this series of 1 over n times n plus 1 will actually converge to 1. So let's jump straight into the integral test for series. Take the following series as an example. So the sum from n is equal to 1 to infinity of 1 over n squared. This is a very special series actually, but that doesn't matter for right now. So we want to know, does it converge? And if so, what does it converge to, right? These are one of the two biggest questions you can ask when looking at an infinite series. So first, let's compare the sequence to the following function in its graph. All right, you could say this is the quote-unquote corresponding function to this, right? Since instead of just being some kind of discrete function that only takes in natural numbers, this takes in all real numbers, except for 0. So this is the graph for the function f of x is equal to 1 over x squared. Well, let's draw in some boxes, okay? Now this probably looks pretty familiar from back when you first learned about integration, specifically an area under a curve. If you notice, this is actually a left-handed Riemann sum of the area under this curve. So that means that this is as you can tell, a pretty big underestimation of the area under the curve. However, look at how what's special about these boxes. This is 1 times 1 which is area of 1. This is the height of the function at this value, which is 1 over 2 squared, which is 1/4, times the width, which is 1. Same here, 1 over 3 squared, which is 1/9, times the width, which is 1, etc., etc. So we got 1 plus 1/4 plus 1/9, etc., etc., until infinity. That should probably look very familiar to you, since the previous sequence, the first three terms are 1 plus 1 over 4 plus 1 over 9. So as you can, like I said before, this is a left-handed Riemann sum from 0 to infinity of the function 1 over x squared. The actual area of this function, as you probably know, from 1 to infinity is 1. However, note that this is from 1 to infinity, as in this entire box is not counted. So from here to infinity, the area is 1, not including this region over here. Alright, like I said, this is not equal to piece with area equal to 1. So we can add the area of that chunk, giving us 1 plus the integral from 1 to infinity of 1 over x squared dx is equal to 2. And since we know that the sum of 1 over n squared is a left-handed Riemann sum, and therefore an underestimation of the area, we know that it's less than this term, right? Well, technically less than both of these terms, since it also includes the 1 at the beginning. We can set up the following inequality. This sum over here must be less than 1 plus this integral over here, which is equal to 2. What we can then, in turn, figure out about this series, is that it must be less than 2, or at least it must converge to a value less than 2. And as you can tell, we've clearly also figured out that it converges. So using this kind of geometric logic for other series, we can come to the following conclusion. Assume that f of x is a continuous, positive, and decreasing function on the interval 1 to infinity, and that a sub n is equal to f of n. Then the series of an from 1 to infinity is convergent if and only if the corresponding integral of f of x from 1 to infinity is convergent. If the corresponding integral is divergent, then the sequence is as well. In math terms, this would be if this integral converges, then so does this series. And if that integral diverges, then so does this series. It's a very powerful tool for very specific types of sequences of series, as we'll see. So here's a practice problem. Does the following series converge or diverge? You might have experience with this sequence before and know that yes, this series diverges. It's the harmonic series, and you probably covered it by now. However, we can use the integral test on it. So we know that this function is positive on the given interval, and it is continuous, while also constantly decreasing. Since it meets all of our requirements, we can use the integral test. Just by looking at the graph of 1 over x, you can tell that it is decreasing and positive in the first quadrant, and it's also continuous except for at 0, but that's not in the interval that we're looking at. So we'll now take the integral of this function on the interval 1 to infinity and see what it yields. So, as you expect, this integral completely diverges. So from 1 to infinity of 1 over x dx will give you the natural logarithm of x, and by skipping a few steps, since you guys know how to integrate this, you'll get that the limit as t approaches infinity of the natural log of t will be the value of this integral. And that clearly diverges. It goes to infinity, and hence so does the series. Now here's another practice problem. Is the integral test applicable on the following series? If so, does it converge or diverge? Now this looks pretty complicated, right? But really, we just need to apply the requirements and see if the integral test works on it. If they do work on it, that's when we've got a bit of a mess on our hands and we've got to carry out an integral. So here's the solution. First, we need to check if this function is continuous on the given interval. This can be quickly done by seeing if there are any x values that make it discontinuous. It is continuous on this interval, so we must test the second and third requirements. So as you can tell, oh, my apologies, I should have replaced the x with an n. But as you can tell, this series, or I guess its corresponding function, is actually continuous in the first quadrant. There are no values of x that will make this function discontinuous. So now we need to see if it is decreasing. We can either do this by taking the derivative and checking to see if at any point it becomes positive, or by looking at the graph. Using either of these methods, yields that this function is not always decreasing. So this is probably very difficult to see, but this function is actually dips under the graph over here and increases again, crossing it several times. And if you want an even more obvious example, well, near the beginning, it's already increasing. However, I'm not sure if it's still increasing once it crosses the point x is equal to 1, which is why I highlighted this point over here. So we could have really just stopped with that requirement right there, because that one, because just by violating one of the requirements, you already know that you can't apply the integral test. But I guess just for fun, we can apply the last requirement. So we need to see if it's always positive. So based on the graph before, we can see that it also isn't always positive, right? Let's go back to that graph. We got that little dip there, which clearly goes into negative numbers. Therefore, it's not always positive. Since it violates not one but both of these criteria, we can safely say that the integral test is not applicable to the series. Thanks for watching another EDD Academy video. I'll see you guys soon. Bye.